Good afternoon, everyone. Welcome to the Statistics Former Student Network webinar for this month. We're very excited to have with us today Dr. Yulia Marchenko. She is the Vice President of Statistics and Data Science at Stata Corp. She received her master's in statistics in 2004 from our famous Texas A&M University under the supervision of Jim Calvin, and her PhD in statistics in 2010 under Mark Genton. She joined Stata Corp in 2004 and has been with the company for almost 20 years. That's pretty amazing. She has more than 25 years of software development experience, and her primary responsibility is to oversee Stata's scientific software development. Her statistical areas of interest include Bayesian analysis, multiple imputation, meta-analysis, multi-level modeling, survival analysis, power analysis, causal analysis, skewed distributions, and many other areas of statistics, including biostatistics and econometrics. So welcome, everyone, and welcome our speaker, Dr. Marchenko. Please take it away.
Thank you. Hi, everyone. Thank you, Marcy, for this nice introduction, and thank you for having me here. I am very excited to connect with some of my fellow egg statisticians and share some of what I've been up to since graduating. Now, I'm going to go ahead and turn off my video for now just to conserve bandwidth. So we have a seamless presentation here. So I've had a passion for programming since high school. And then later during my undergraduate studies, I developed a passion for statistics. So combining both in my career was really a dream come true for me. I usually present various statistical topics, but lately I've been asked to talk about statistical software development and some of its aspects, such as software reproducibility. Regardless of our statistical areas of interest, we often need to write code. And sometimes we may want to share this code with others. So I thought that talk about statistical software development might be a good choice for this webinar series, given its diverse group of statisticians. In my presentation today, I'll share some tips and tricks for how to produce high-quality software with an eye toward software reproducibility. Okay, so here's a quick, hold on. Here's a quick disclaimer that the views in this presentation are my own and don't necessarily reflect the views of Stata Corp. And here's a brief outline for my presentation. I'm going to describe in detail the main stages of professional statistical software development, focusing a little more on reproducibility. Okay, before we jump into talking about the main stages of professional software development, let's talk about who are those people who want to produce or develop statistical software. Researchers who work on their new methods may want to implement software that accompany those methods to integrate it into practice. Professionals who work in certain organizations and often need to write some specialized code might want to share this within their organization, or they may even want to share that code outside their organizations. Practitioners who need to use a certain method that perhaps has not been implemented in any software yet, they might be interested in implementing it and potentially sharing it with others. Of course, consultants often need to write code on demand. And finally, commercial software providers do focus on developing statistical software. Okay, so many of us can combine our programming and statistical skills to write statistical software. But what does it mean to produce a professional statistical software? there is this something more that we need to do to make our software professional. And I'll describe what this more in this presentation. Now, I also wanted to point out that when I say professional software development, I don't necessarily mean commercial. I just mean high quality software. When I think about professional statistical software, here are the attributes that I like to see. First and foremost, your software must be reliable, meaning it must produce correct and accurate statistical results. And those results must be stable across different runs of your software or across different operating systems. The software must be reproducible so that whenever users are investing their time in learning your software and learning the syntax, they are guaranteed that many years later, they can still reuse that old code that they developed early on in the newer versions of your software. Professional statistical software need to be efficient, where it strikes a good balance between the speed and the use of memory and disk space. And it really must be consistent so that the same concepts continue to be accessed in the same way so that it minimizes the learning curve for your users. It is good for the software to also be extensible so that others can build on what you've developed initially and potentially improve it or implement a new method based on it. And it is important for the software to be well documented. Making your software easy to use will definitely be beneficial, and this can be done by either providing some point-and-click interface that helps users learn your software. You might even consider providing your software in various languages, depending on who is your intended audience. And another step, which is often overlooked by us because of the lack of time, is what I call polish. So these are these last checks that we do for our software that make it stand out, that make it high quality by considering different careful error traps, by making sure that the error messages we produce are clear and intuitive, by checking that the output we produce is clear and consistent and delivers all of the information that we want about our statistical method. And of course, for the software to be widely used, you do want to provide a good support for it. Before we talk about each of those aspects in more detail, I wanted to kind of like quickly outline how I like to approach adding a new statistical feature, which I thought might be useful for some of you who are just at the beginning of developing some of your code. So first of all, we do want to acquire deep knowledge in the statistical area of interest. And if you're a researcher, you probably already acquired that as you were working on your method. But for a practitioner who is not familiar with a certain method, there is initial time investment in understanding the statistics behind it. Next, I like to focus on identifying which features and which methods I actually want to include as part of my software. Sometimes as researchers, we focus on very specific aspects of our project. Say we're implementing a new estimation method, and of course we want to develop code that checks that our model parameter estimates have good finite sample properties and so on. But when we later decide to release this code to others for use, we really need to think about, okay, what is the potential workflow of analysis that a practitioner might want? or need for publishing a paper or for making certain conclusions from their research objectives? Do they only want to get estimates of model parameters, or maybe they also want to get a prediction? Maybe they also want an easy way of obtaining linear on nonlinear estimates of model parameters. So as a software developer, you need to consider a full picture beyond what might be needed, say, for you to publish a paper. And once those features are identified, I usually start implementation, although I like to start with some prototypes where I just outline some of the algorithms that I want to implement, and I implement it enough to make sure that I know what I'm trying to do is feasible. And then I actually like to step back and look at how these algorithms and features are going to be presented to the user, because this way it helps me sometimes to structure my code differently, or even have a different timeline for different implementations of my code. And of course, it is important to spend sufficient time for verifying and certifying your features that you are adding. I also like to do it concurrently with implementation, so that anytime I add some new code or some new portion of the algorithm, I have this test script that I fill in with the corresponding tests that are checking the correctness of the code that I just developed. And the documentation is very important. I usually collect some of the ideas for the documentation at this first research step, because usually we read lots of papers at that time, and we may have some ideas for some good motivation for the method we're implementing. We may have some good ideas for examples we might use. This is all becomes very helpful at the time you're ready to start documenting your software. And optionally, in Stata, we also provide graphical user interface for all of the features that we develop. So it is important to coordinate that with the developer who does it, because often you have to revisit the features that you're adding from the point and click user interface perspective as well. And this last step, polish, as I mentioned, is something that we do something that I do at the very end, is to really kind of like put the bow on the present and make sure that users who are gonna use my software is gonna have like this really good initial experience. So the output is very clear and understandable. Any error messages that they get are understandable, and they're also consistent in style with other existing features. So this is just a quick overview of the terminology. You might hear me say the word command or options in this presentation, and so I wanted to quickly explain what it means. So commands are how Stata users interact with the software. In other software, this might be a package or a procedure or a function. So for instance, if I want to feed a linear regression in Stata of variable y on variables x1 and x2, I would type regress y x1 x2, and here regress is the command name, and then what follows that command name are the command arguments. Now, options are something that are specified after the command arguments following the comma. So in my first specification here, by default, I get, say, 95% confidence interval for the estimates of my regression parameters, and I get classical standard errors. But if I wanted to change that and say I wanted the command to report 90% confidence interval and use, say, robust standard errors, I can specify it through options. Okay, so let's talk about those main stages that I mentioned earlier. And we're going to start with efficiency and reliability. How can we produce efficient and reliable code? In terms of efficiency, of course, there are often trade-offs between speed and space. If you have to decide which way to go, you really need to think hard about your intended audience. Are you writing this for researchers who might have limited computing resources? If so, in that case, they might be willing to wait longer for the results in favor of conserving disk usage or memory usage. But another group of researchers that have lots of access to, say, RAM, they may want their results faster and they don't care about the memory consumption. Sometimes you can offer both approaches. For example, in MEDA, which is Data Matrix Programming Language, we sometimes do offer users to choose whether they want to favor speed or favor memory usage in different computations. But this typically requires implementing your algorithm in different ways, so it takes additional time. And of course, regardless of the efficiency of your code, you must write accurate code that produces accurate and stable results. What are some good programming practices? You might want to try to avoid duplicating code. If you have some portions of the code that you need to reuse, it is better to implement it as a standalone function and then simply reuse it from the appropriate places in your code. This will minimize any mistakes that you may propagate by duplicating code. And if you need to fix something later, this will also make it much more easier to do. It is important to perform computations in the highest possible precision. And of course, you need to think about the operation. When you determine what's the highest possible precision, it is determined relative to the operation you're trying to perform. Many languages provide you more speed benefits if you can vectorize your computations. For instance, if you can turn a loop over observations into a matrix operation over the observations treated as a vector, you might gain some speed automatically, depending on the package that you are using. I cannot emphasize enough how important it is to comment your code. Even though it might be very clear to you what your code does at the moment you're writing it, when you go back to your code 6 months later, or if someone else is trying to extend your code, having comments in your code becomes extremely important. It is also important to use consistent coding style and readable function names when you're developing your code so that others can more easily read it later and extend it. Pay attention to handling some edge conditions and errors gracefully. When you develop your code, it's nice to keep backward compatibility in mind as well as reproducibility, and we'll talk more about it later. And of course, you also need to keep numerical accuracy in mind when you're performing certain computation. For instance, depending on the calculation, you might want to perform it in the normalized scale, or maybe that computation needs to be done in the log scale to ensure that you have the highest accuracy. So once you implemented your code and you're ready to test it, here are a few tips that I like to share regarding certifying and testing the software. As I mentioned earlier, I do like to develop test scripts as I go rather than waiting when I implement everything I implement all of my code and then start building some test cases for it. The first step would be external verification. So you want to find some known benchmarks. That might be published results, that might be some external software. Maybe it's possible for you to rederive your results independently using some alternative derivations and verify your results against manual computations. And of course, often we try to verify, do external verification by using simulation. It is also important for you to test your code. You know your code best. You know which tasks you need to focus on more and which tasks would pretty much use the same code. And so it's sufficient to include only one type of testing. But it is also important for someone else who is not familiar with your code to test it, because again, you know your code so well, and sometimes you may not even just stop to think to exercise certain cases because they just don't make sense to you. And you know that these cases are not possible, but that's where mistakes can happen because users who don't know your command very well are likely to explore those cases unless your software precludes them from doing so. And then the next step is certification. And this is one of also important steps here at Theta, is to make sure that as we develop or extend our code, the previously verified results do not change. So, and the certification essentially verifies that from run to run of your software on different architectures or different platforms, you do get results that are agreeable within a certain precision. So unfortunately, certification is really feasible for languages or software that provides some programming or scriptable environment, because you really want to automate that step. To certifying against verified results, you usually find example with some known answers. These can be benchmarks, this can be previous simulation results, but you have some numbers that you trust. And then you write a script that compares the results that your software produces with those established benchmarks at the desired level of precision. And if anything in that script is violated, the script stops and produces a report of all of the encountered problems. To make things a little more concrete, I will use Theta as an example, but you can really replicate this in any software of your choice. So Theta offers our users some tools that help with certification by providing some built-in tools that are designed to make the writing of certification scripts easier. For example, here I'm creating my certification script called myReg. And in that script, I load the data set of verified values, and I run. Suppose I want to write a certification script for regress, and this is just a very, very simple example here to give you some flavor of what I'm talking about. So I run regress on variable y and x, and I want to test that the coefficient for x doesn't really change from that previously established correct value. So I use the assert command to check that the relative difference between the bench value for the regression coefficient of x and the value produced by the regress command is no more than 10 to the minus 8. And this relative precision here is you determine really how tight you want that limit to be, depending on which operating systems you're looking at and which type of computation you're trying to certify. And here the next step, it just test that, okay, options that are not supported by regress, regress should issue an appropriate error message in that case with an appropriate code. And if everything passes fine at the very end, you will see that everything is well with that script. And you can read more about certification in this reference here. So let's now talk about reproducibility. And really, reproducibility is an potentially overused term. Different people may mean different things when they talk about reproducibility. Usually in science, we think of reproducibility as a way to obtain the same results repeatedly under the same conditions. But some people may think of reproducibility as a way to replicate published results, for instance, using some new data. Or some may even think about it as merely an automation of certain tasks or reports. So really the steps of how to achieve reproducibility and the meaning of what are these same conditions depend on the type of reproducibility. Here I will focus on software reproducibility, which essentially requires scientific reproducibility. And it is important to distinguish between the exact reproducibility. Do we expect the results to be exactly the same? Or do we want results to be reproducible within some finite precision, where we want the results to agree within some predetermined tolerance that is acceptable to us? So we can further think about scientific reproducibility as stochastic reproducibility, numerical reproducibility, computer reproducibility, backward compatibility, and integrated version control. So with stochastic reproducibility, we want to produce the same results from a stochastic procedure repeatedly. Well, stochastic procedures depend on random numbers. And so every time you run your software, you are going to get slightly different results, which is absolutely expected from a stochastic procedure. But if for some reason you want to make sure that you can reproduce those results, it is important that your software provides a way to generate the same sequence of those random numbers after each repeated run. And that's usually achieved by setting a random number seed. So you would not want to set a random number seed manually in your procedure, but you may want to provide a way for users to do that. And if you perform computations in parallel, it's also important to keep in mind that to ensure that the sets of random numbers being used by each processor are truly independent, you really need to use random number streams, in which case for reproducibility you will need to set the seed for each of the streams. Numerical reproducibility, I like to think about it as a way to produce the same results from a deterministic but possibly iterative procedure. And this often comes up when users are trying to compare results from different software packages, and whenever those results are based on this iterative procedure or any numerical procedure, whether you can get exact results will depend on how the procedure is implemented and how does the software specify stopping criteria for that procedure. Are the computations depend on operations potentially, in which the order in which your data are in before you run the procedure is going to have an effect on the results. So, and also whether you perform computations on a computer with a single core or multiple cores, you might see some slight numerical differences. just as you would see them if you run your procedure on different computers. Which brings me now to computer reproducibility. And this is really a way to produce the same results across different computers and operating systems. It is very closely related to numerical reproducibility, but as many of you know, different computers have different chips and libraries, so they may perform certain basic operations slightly differently. Operations performed on single versus multiple cores might be slightly different. So truly, the exact computer reproducibility is rarely possible across different platforms. But for stable results, stable computations, you should always expect some finite precision of reproducibility here. And now the final step, which is a little trickier to achieve, but I think it becomes extremely important to ensure reproducibility, is the so-called backward compatibility. And I will focus on backward compatibility achieved via integrated version control, or IVC for short. So this is the ability to produce the same results in the future when you use the same software. With IVC, you can write your code in a way that can run reproducibly many years later, even in the newer versions of your software. It is important to distinguish IVC from source version control, which simply helps you track changes of your code over time. And IVC is also not just a container that bundles the existing software and operating system to run on other infrastructures. Genuine IVC requires careful and often time-consuming physical merging of all of your existing software bases over time. And as far as I know, I think Stata is the only statistical software package that offers integrated version control. So as a user, you can access your old syntax or old results by simply prefixing your old command with the version statement. Or you can specify that version statement within a program. Also, as a programmer, Stata offers you some built-in tools that can help you track different versions of Stata and incorporate that as you're writing your own code that expands some of Stata's built-in features. So here, just as an example, I'm showing you that in the modern Stata, which is currently Stata 18, if we wanted to produce binomial confidence intervals for the proportions of variables y1 and y2, we would type CI proportions y1, y2. But prior to version 13, we had a different syntax for computing this confidence intervals. And you can still use that old syntax in the current modern version of Stata 18, but all you need to do is simply prefix that portion of the code with the corresponding version where that syntax existed. It is important to note that IVC is not a time machine, so it will not version control incorrect results or behavior. And this is really what you want from modern software. You want to be able to use your old code, but for that old code to still benefit from some of the modern improvements, such as fixing any potential bugs or problems, or maybe a new random number generator is a better random number generator is available. So you might want your old code to be able to use those improvements. And you can read more about IVC on this website here. So going back to the definition of the scientific reproducibility, now that we went over some of the aspects of scientific reproducibility. What do we mean when we say under the same conditions? So really, if we want exact scientific reproducibility, we need to consider the same operating system and computer setup, potentially the same implementation of the procedures. For iterative procedures, we need to make sure that the same stopping criteria are being used whenever we try to reproduce results. And for stochastic procedures, for instance, we need to make sure that we hold on to the random seed that was used to produce the original results. There are more things that we might need to keep in mind. So having said all of that, exact scientific reproducibility may not always be feasible, but for stable analysis, you should always expect at least finite precision reproducibility within reasonable tolerance. So how would we go about incorporating this reproducibility ideas when we are writing our code? So if you're working on a stochastic method, it is important that you provide a way for the user to give you a random number seed. And if you're using streams, then you will need to be able to provide that for all streams. You never want to hard code the random number seeds in your program. Now, if you're working on some algorithm that depends on the sorting order, you might need to decide whether you want to make that algorithm sort order independent, or it is important for this algorithm to depend on sort order, in which case you need to provide additional tools for users to be able to reproduce the results that depend on sort order. And yes, if you're trying to match other software, then you need to make sure that you use the same stopping and convergence criteria in your implementations. And it's also important to keep in mind when you're performing certain operations, what would be the best numerical way to go about those operations. For instance, adding very small numbers and very large numbers in different order might lead to numerical differences. And as we implement our methods, it's important to keep that in mind. And of course, as you're developing your code, it is important to think about backward compatibility and version control. Are there any things you can do to make sure that if you're extending your current code that was already released to some users, to make sure that you don't break their current scripts? Now, another aspect is consistent software. And it is probably a little harder to achieve that if there is no centralized way of ensuring that consistency. But I think it's still important for everyone to keep this in mind. Say if you're working with a group of developers on some bigger software, it's nice to at least establish consistency of the methods within that project. And just an example, for instance, what I mean by consistent software, say state of release the regression command with the syntax where you specify dependent and independent variables following the command name. And now we're working on the logistic regression, for instance, and we want to implement that. Well, we would want to specify the dependent and independent variables in the same way as we did, say, with regress, rather than suddenly changing to specifying these attributes as options, for instance. Because once the users learn the structure of your command, it's nice to maintain that structure for all of the other similar commands, because that reduces the learning curve for them. And same with naming of options or arguments of your programs or functions. Try to maintain consistency. If you decided to that say the option that specifies the confidence level is called level, try to maintain that name across all of the functions that you produce rather than say call it CI level or something else in some other instances. And keep in mind when you're writing your code, keep in mind the extensibility of your code. It's good for you to write your code in clear style and use consistent style. And different software packages offer different tools for that. For instance, data users often just follow our official code that they can access. Now, we're not an open source software, but we are what we like to call open development software. So there, all of our do files and many of our meta files that implement different procedures are available for our users to have access to and extend, and they can see them by typing command view source. And that really helps them follow our style in their new programs that they are writing. As I mentioned earlier, comments are very important to include in your code. And it's nice to also follow the syntax of already established tools. In Stata, we provide built-in tools such as syntax command for parsing utilities for our users, and that's exactly what we use when we design syntax for our commands. So technically, Stata users can replicate our syntax very easily. It's important to write generalizable code where you don't hard code names. I know it's a silly example, but say if you have an outcome variable, don't really hard code its name. Make sure that people can supply the name of that variable. And try to write flexible code. If your method requires some initial values for some parameters, well, provide the tools that allow users to change those values. It is important that some of the intermediate results that you have and everything that you actually output are stored somewhere by your method and accessed programmatically. If you develop some procedures that might be useful for others, it's nice to perhaps develop them as standalone utilities that can be used later by other developers as well. And in Stata, we have some tools that we develop like that, that we share with our Stata users, and they're documented in that help file. And it's also important to structure your code when you're writing your software such that it can, people who are adding some methods to it can benefit from some of the built-in computations. For instance, Stata's power command is used to do power and sample size analysis, and it offers many built-in methods. But it also provides features for users to add their own methods. And when they do, all they need to do is to just write a simple computation that computes power and sample size. And then Stata has a way of handling multiple values and automatic generation of power curves for the user automatically. So they don't have to worry about writing for loops or anything to take care of multiple specification of parameters. Good documentation is extremely important in how widely your software is going to be used. This is essentially the first impression that someone who tries to use it is going to have. And if your documentation is poor or unclear, the chances are that people are not even going to try running your method. So I like to think that a minimum for a software documentation is you have to include a description of what your procedure does, and you have to carefully describe all of the options and all of the features of your procedure. You must include underlying methods and formulas and provide the references for those methods and formulas or for anything else your method relies on. And of course, including examples in your documentation will make it much easier for people to adopt your software. Now, additionally, for instance, in Stata, I like to see more out of our documentation. And of course, in addition to describing everything I said above clearly and concisely, I like to provide some brief motivation in introduction for the implemented methodology. We like to provide detailed examples of different usages that span different fields and different applications. We like to describe the output and interpret the results that people get. And it is important that the documentation is comprehensive, but yet concise. And if you're one of those lucky people who could write in an entertaining way, this always goes really well with the users too. Now, really quickly, how would one go about writing good documentation? First of all, consider your audience. Are you releasing your software to a small group of researchers who are already experts in the area and are familiar with lots of terminology and usage? Or do you want to appeal to a wider public who might not be familiar with your methodology? It's for the latter, it is important to avoid using jargon, and it's easy for us to assume the same knowledge from the user as we have after working on this methodology for many, many months. But it is important to step back and make sure that all of the terms are defined clearly in your documentation. Rather than resorting to formulas, it's nice to try to find some intuitive explanation of what your method does and have the more technical exposition be part of the more technical section, such as methods and formulas. And it's nice to do some extra research for various applications in different areas of statistics. It's important to strike a good balance between comprehensiveness and conciseness. And I always emphasize to people that they need to properly cite all of the sources, especially when we're working with some data. It is important to try to find the original reference for the data rather than just citing the methodological paper that used it. And if you're interested in kind of seeing some examples of our documentation, you can follow that link. Making your software user-friendly can be beneficial. As I mentioned earlier, of course, if you provide consistent and convenient specifications, that will make it easier for people to learn. If you provide good documentation, it's going to make it easier for users to learn it. And it is important to polish your software. I'll talk a little bit more about it later. And it's nice to provide a graphical or point-and-click user interface. Many people look down on it, but I always find it really helpful and very efficient, I must say, in learning some of the new commands. For instance, in Stata, when you use point-and-click interface, it actually shows you the command that it used to that the dialog box produced, and you can later use this command or modify it easily interactively or even include it in your script. So don't discard the beauty of graphical interface. So polishing your software. this is probably the most tedious task of producing a high quality software, because usually by this time, when you reach this stage, you're already out of time. There is very little left, and it's very easy to bypass that step because of that. Well, I like to remind our statistical developers that unfortunately, even though this is the last step in our development cycle, this is actually the first step of users having experience with your software. If they try your software and they don't understand the error messages that you produce, or they specify certain things that were supposed to be precluded and they get results that they didn't intend, if they see lots of misspellings in your output, or they can't understand the output you produce, the chances are your software is not going to be used. And all of that effort that was put into it, all of the research and all of the implementation of the algorithm might not be fulfilled as much as you want it to. So this step is important in making your software as high quality as possible. And of course, providing software support is important. When people invest their time in learning your software, they want to have their questions answered promptly. They want any problems that they report to be fixed promptly. They want some additional information about different usages of your software and how they can incorporate it in their analysis. So depending on what you want, depending on the intended use of your software, there are lots of things that you might consider that can promote it and make it well supported. So just to conclude my presentation, I find producing professional statistical software impactful, challenging, and definitely rewarding. It unites practitioners and researchers from different disciplines and exposes them to many statistical areas. So that was the reference that I mentioned earlier, and that's all I have for you for today. Thank you very much for your attention.
Thank you, Dr. Excuse me, I apologize. Dr. Marchenko, that was awesome and give us a lot of tips for making excellent software. Is there anybody in the audience who has any questions they'd like to ask Dr. Marchenko? It was nice that you were able to give us some tips on some of the things you do at Stata, but also using some of your code that's available there to do some reliability checks. That's nice.
Yeah. It's definitely a very specialized niche of statistics, and but yes, I find that dealing with software and writing code, it's so much more, it happens so much more often these days than even when I was in the program, that it's worthwhile to invest some time into getting some tips and tricks on how to do it.
Great. There's someone in the audience who's raised their hand. Atik?
Hi, this is Atik. Dr. Marchenko, I have a question on the testing part. I'm not fully familiar with the Stata program, but I wanted to understand, if a user writes a function on Stata, does Stata helps in the testing part?
So we have, when you write as a user, when you write your own method in Stata, you often submit it to statistical software component that that is hosted by an independent party. And when you could submit that function, or we call them commands, to that component, usually they ask you to provide a certification script or your testing script that you developed. And at that point, they can give you some feedback on what you might do differently. But we officially don't test all of our user software. We definitely test all of our software that we put in officially. But users are always welcome to write our technical support if they have any questions or concerns, or they want some tips or feedback on their certification scripts.
Thank you. I have one more additional question on the documentation part. So I program in Python, and I'm currently helping my team in developing a model. And after the model is developed, I will have to like connect with the developers and transform my code to the production. So I'm right now working on the documentation part. I have some part of documentation as a README file in the script, and some form of the documentation in the form of PowerPoint. So how would you suggest to structure the documentation part? Should I have a different form of documentation that I need to present and some in this part of the script?
So I'm not very familiar with how documentation is done on Python. So you would probably have to check what are the requirements that they have for the supporting materials for the software. Typically, you would have to include the kind of like the structure, the specification of your function, and all of the arguments that you have in that function. And my guess, it would have to be described probably beyond just the README file, because it will include many more information that might be needed. And then I don't know if Python necessarily requires you to include examples of your software usage, but that I always find this useful to do. So you might consider doing that. And then you can also have some additional materials, for instance, some PDF document that shows different usages located somewhere on your personal website, or something that you link to from the description of the your README file that you submit to Python for people to get more information.
Thank you. And one last question. So if you are pulling data from an external source, then let's say it has like 20 or 30 columns, and for your production, maybe you are using only 5 out of them. So for the documentation part, would you recommend defining all the terminologies and all the columns in the data set, or only the ones that is being used?
It really depends. If the data set becomes really big and you're not using all of those columns, it may not be as useful to define all of them. But if the data set is fairly small, there's no harm in just listing and explaining all of the variables in your data set.
Thank you.
Thank you, Dr. Marchenko. Does anybody else have any other questions? We're closing in on 2 o'clock, so we might have time for one more quick question if somebody has one. Well, thank you, Dr. Marchenko, for joining us today and sharing with us all of your work there at StataCorp, and helping us grow as programmers. Maybe do better programming jobs moving forward. I think we probably all have some aspect of that in our lives, maybe some more than others. So this is all very useful information and tools to use moving forward. Good practices.
Thank
Welcome.
you very much.
Awesome. All right, and I guess we'll sign off now, but of course everybody is invited to, the next webinar. It'll be published soon if it hasn't been already. Looking forward to a talk next month as well. So keep your eyes and ears open. And thanks for joining us today. Happy holidays.